Good morning. My name is Samuel Jero, and I'm a member of technical staff at MIT Lincoln Laboratory. Today, I'm going to be talking about our work on practical principle of least privilege for secure embedded systems. This is joint work with a number of my colleagues from MIT Lincoln Laboratory, as well as collaborators from George Washington University and Draper Laboratory. Now, the focus of this work is on embedded systems, which come in a variety of forms and can be found in everything from the power system to factories, to planes and trains, and even the cars we drive. But one of the important things to realize is it's not just the number of these devices that is increasing, but that also the tasks they're being asked to do are becoming dramatically more complex with things like autonomous driving, machine learning, image processing, distributed coordination and control algorithms becoming increasingly popular in these applications. And then, of course, the fact that these devices are controlling actual physical objects, which means there's a pressing need for security. Now, one of the promising techniques for providing security in embedded systems are microkernels, where the key idea here is that we want to minimize the amount of code that executes in the kernel in kernel mode. And this is done by removing everything from the kernel except those components that actually need to operate in kernel mode to achieve the system's required functionality. And this typically results in a very, very small kernel with minimal functionality, and then all that functionality implemented as a collection of many services running in user space, where each of these services is a separate process and they use IPC for communication. So for instance, instead of most drivers being part of the kernel, they're now separate applications, separate processes in user space at lower privilege, but also isolated from both the kernel and from each other. Now, this would seem to make microkernels ideally suited for high criticality embedded systems. Unfortunately, although we've had several decades of experience working with microkernels, they have yet to see general adoption in embedded or general purpose spaces. And a large part of the reason for that is that there appears to be this mismatch between what microkernels provide and what applications want. So microkernels tend to provide APIs with really minimal building blocks for systems and very low levels details. So these APIs focus on things like threads, scheduling, memory management, paging, IPC, and interrupts, and operate at very low levels where really even paging is left up to user space. Additionally, there's no even minimal peripheral support for basic things like even timers or simple I/O. Device drivers are left up to applications, which makes a lot of sense because like a device driver is really just another user space process from the microkernel's perspective. In contrast, applications really want to focus on their application logic. They definitely don't want to deal with finicky things like memory management, paging, and writing their own device drivers. And also with the increasing complexity of the tasks these applications are designed to do, and the fact that we're seeing an increasing number of interacting components in these systems for things like machine learning, image processing, and these distributed coordination control algorithms. And all of this really comes together to need some kind of high-level API to fill this gap and simplify development of these systems. Now, historically, there have been two major approaches to doing this. The first of these is a library API approach, where one or a collection of libraries implement this high-level API, and these libraries are all linked into all applications. SEL4's user space libraries are a good example of this, where there's a library to do memory management, there's a library for memory allocation, there's a set of libraries to implement device drivers, and things of that nature. Unfortunately, this approach has a major difficulty with communicating and coordinating between processes, and especially multiplexing hardware between multiple processes, because like the device drivers are all built into each application. The other primary approach is what you might call a single monolithic API service, where you have one single service that implements your entire high-level API for the rest of the system, and that all applications talk to. This is the approach taken by Workspace OS and Grail OS for their OS personalities. Unfortunately, this API service becomes a single point of failure and really tends to centralize privilege, defeating many of the benefits of a microkernel approach. Instead, in our work, we chose to implement this high-level API as a collection of services where each service is responsible for a separate part of the API. And this is really motivated by the principle of least privilege, where every program should operate using the least set of privileges necessary to accomplish its job. And this tends to result in a number of many small services, each doing one particular job. Now, this might seem like a fairly obvious design. So the key question really in this work is this design practical, especially from a performance overhead and real-time predictability perspective? And what we find over the course of this work is that this is in fact a practical approach. We demonstrate it on 2 different microkernels and then compare its average and worst case performance to real-time Linux, finding it to be better or comparable. Okay, so far we've covered the motivation for this work. We're now going to talk briefly about our API that we implement in this work called Patina before we dive into the 2 implementations of this API, one in SEL4 and one in Composite. We'll then cover some evaluation results and conclude. Okay, so in this work, we develop a high-level API that we're going to use for our implementations. We call this API Patina. And it's really designed as a prototypical RTAS API. So we wanted it to be simple and OS independent, but otherwise it's not particularly novel and very similar to the kind of things you find in common RTASs. Our API has 7 major components. We have process and thread management. We have channels. We have timers and time, synchronization, which in particular we provide mutexes and semaphores, event handling to let other elements of the system notify applications about events, for instance, timers firing or channels being ready. We also have memory management and then some basic I/O. While we don't have time to cover the full details of our API here, you can look at the paper for a complete list of all functions in our API. Okay, we now turn to our first implementation of this Patina API on SEL4. Now, SEL4 is a microkernel of L4 heritage, and it's out of the University of New South Wales and NICTA. And its major claim to fame is that it is formally verified, which means there are functional correctness, integrity, and information flow proofs for this system, as well as a proof of the correctness of the compiled binary code on ARM. And what this formal verification really tells us is that SEL4 is guaranteed to correctly implement its specification and to be free from large classes of bugs, most notably memory safety bugs that have caused numerous issues for other systems in the past. Among the key characteristics of SEL4 are that it's a capability-based system. Now, a capability is simply an unforgeable token that gives access to some resource. A familiar example from Unix would be a file descriptor. And capability-based systems really take that approach and apply it to everything in the system. So everything is a capability. And now on the right of this slide, you see a complete list of all the capabilities in SEL4, from thread control blocks to add memory address spaces to C nodes, which are capabilities to store capabilities, to IPC endpoints, and a number of others. The other important characteristic about capabilities in SEL4 is that while you can use a capability to configure something, for instance, to map a page at an address, you cannot query the current state of the system using capabilities. So you cannot ask, what address is this page mapped at? And that's because doing so would violate the information flow guarantees of SEL4 by introducing a trivial storage side channel. Okay, so how do we implement our Patina API on this system? Well, we implement it as a set of services that we see at right here. So we have an untyped service that handles capability creation for the rest of the system. We have an event service that notifies other pieces of the system of events. We have a loader that handles process and thread management and memory management. We have a synchronization service to handle our mutexes and semaphores, as well as timer and a channel service and then an escrow process that helps manage capabilities on behalf of applications. Now, what you notice here is that usually you have one service per API resource, and this is following the principle of least privilege. Then each of these services is a separate protection domain and uses IPC to communicate with the rest of the system. Further, these services may depend on other services. So, for instance, the event service is used by a number of other services in the system, including the timer service and the channel service for event notification. Finally, we have a small helper library that applications can link to that basically just wraps these IPC calls so that applications don't worry about having to serialize or deserialize IPC messages. Okay, we want to take a closer dive at just one aspect of this implementation, and that's this idea of self-contained processes. And really the goal here is to decentralize privilege in the system by avoiding having any single component in the system that has access to all capabilities for all processes. And the way that works is that self-contained processes, which are all the processes in this implementation, maintain sole control over their capabilities and memory, including all metadata about those capabilities and memory. And this is in sharp contrast to most existing systems where, for instance, you'll have memory management code that handles memory management for all processes in the system, and it's going to maintain data structures about each one of those processes that memory management code owns. In contrast, self-contained processes have the process own that information and have to explicitly delegate it to the rest of the system. And what this is really doing is it's separating past trust in other components from future trust. So for instance, that memory management code has to be trusted to set up the process right. But if you never access it again in a self-contained process system, it never has to be trusted after that point. Now, self-contained processes are very strong, and we do have some ways to deal with malicious processes in here, but I'm going to have to refer you to the paper for those details. Okay, the second implementation of this Patina API we do is on Composite, which is a component-based OS and microkernel developed by George Washington University. Like SEL4, it's a capability-based system, but the similarities really end there because Composite has a very unique thread migration-based IPC mechanism. And this is really where components, not threads, become the core abstraction of the systems, and that threads can actually migrate between protection domains to do IPC. And this is, of course, unlike traditional IPC systems where you block the application thread and start a service thread and so forth. It's also important to point out that this thread migration IPC still maintains strong memory isolation between those components via page tables. Composite also has user level scheduling, which means that scheduling and blocking policies are able to be defined in user space. Now, to implement the Patina API in Composite, we use a design like this. Again, we implement the API as a set of services where you have a capability service that handles capability management for the system. We have an event service that handles event notification for the system, a constructor that sets up the initial set of components and handles process and thread management, a scheduler that does scheduling, as well as being involved in synchronization and timer management for the system. Then we also have a channel and timer services. Much like our SEL4 implementation, each of these components really provides mainly a single API resource. And then we use IPC, in this case, thread migration-based IPC to invoke different services. Also, similarly, these services may depend on other services. So the scheduler provides all blocking and activation for the entire system. One unique element of the design of our Composite Patina implementation is that fast paths for resources are implemented without direct calls to the services. So both synchronization and channels have some shared memory and a library element of them that can be used in the simple common case. And the service components for those only have to be invoked when there's thread coordination that's required or for setting up and tearing down those abstractions. Now, there's a lot more that we could say about both of these implementations, but due to time, we're going to have to move on and focus on our evaluation. In the evaluation, we're comparing three systems, our SEL4 Patina implementation, our Composite Patina implementation, and a baseline Linux 5.4 system with the real-time patch to help us understand acceptable average and worst case performance. Our evaluation system is a Zinc 7000, which is a reasonable proxy for lots of the kinds of systems we're seeing in embedded devices. And we do a micro benchmark evaluation of key performance metrics for several of the API resources, as well as evaluating key performance indicators of microkernels in general. This chart shows a complete list of all of our results and is absolutely overwhelming. So we're going to simplify it initially by focusing on just the core API primitive results here. Now, even this is still overwhelming. So we'll start by focusing on the average case performance. And what we see here is that our Composite Patina pretty much clearly outperforms our Linux implementation. Things are a little bit more mixed in our SEL4 Patina, where channels and uncontended mutexes and semaphores are slower, and contended mutexes and semaphores and timers are faster. Now, if we move to the 95th percentile, things actually get a little bit more clear. Both of our patinas now broadly outperform Linux. And what we can take away from all of this is that these implementations perform well, with performance generally better than or similar to Linux, and that this is increasingly so in the worst case. Okay, so in summary then, microkernels are a promising approach to improve security for embedded systems. However, there's really a pressing need for higher level APIs to meet the needs of application developers. Prior approaches to providing these APIs were limited either in the communication and coordination between processes they could provide, or in causing significant privilege centralization, really defeating the benefit of a microkernel-based design. In this work, we explore a high-level API composed of many interacting services that follow the principle of least privilege in separating API resources into different services. We implement such API systems on two distinctly different microkernels, SEL4 and Composite, and our evaluation demonstrates that this approach is practical and performant, with performance equal to and often better than real-time Linux. That concludes my presentation. I'd be happy to answer any questions now. Thank you very much.